Hi folks, this week's lab is all about buffers, but in order to quantify whether a solution is capable of buffering, one of the things we need to examine is how indicator dyes work, because that's how we're going to read out the pH of our solutions. And indicators are a really cool thing in that they are a very colorful way of seeing which of two forms something will take on at a certain pH. The way that indicator dyes work is very similar to the way that the amino acids have been working, which is that they've got the ability to lose or perhaps gain a proton, depending on which of these two forms they're in initially. And what makes indicator dyes really cool is that usually this change, this loss of a proton, does something to their chemical structure that messes with the way they absorb light. So for example, I might have something that is green when it has a proton on it, but then is blue when it loses that proton. Or if you think about something like phenolphthalein, which we've used on a few little titration experiments, we've examined that situation where it is colorless with the proton on and then turns a bright pink with the proton off. The cool thing about this is that when you reach the pH that is equal to the pKa for that indicator dye, you're going to be in between these. When this is true, then my concentration of HIND is going to be equal to my concentration of IND minus. And when that happens, I'm going to get a color somewhere in the middle. If I'm substantially more acidic than that, then I've added H+, that's going to force H's onto my indicator and turn it green. And if I deprive myself of H+, if I'm in a very basic solution, much more basic than the pH that would equal its pKa, then I'm going to force the reaction this direction and wind up with it looking blue. Now, different indicators have a variety of different cutoffs, and any one of them is only going to tell you a limited amount about the pH of your solution. But if we stack up several of them, we can get a little more specific information. So we're going to use this as an example. These are three indicators that are not involved in the experiment that you're doing this time. I'll show you them in just a moment. But these three indicators, malachite green, cresol red, and bromophenol blue, each have a color change range, and they're represented here. Malachite green, in fact, has 2 acidic protons, so at very acidic conditions, 0.2 and under, it's yellow. Between 0.2 and 2.0, it becomes green, so if it's yellow-green, you're somewhere in here. From 2.0 up to 11.6, it's in one specific form, and so it's always green. And then as you go from 11.6 to 13.2, that color drains away. And above 13.2, it's completely colorless. Cresol red and bromophenol blue just have a single color change region. So each of these are yellow underneath this specific pH. And then there's a range where they go from, in the case of cresol red, yellow at 7.2 up to a sort of rust red around 8.8. And then from 8.8 upwards, you're looking at that color. Bromophenol blue is a much more acidic pKa, and so it's from 3.0 to 4.6 that it changes color, going from yellow to purple. Anything above 4.6, it will be purple in color. And so we can use these ranges to sort of narrow our way down to a specific result. So for example, if I tell you that a solution of HNO2 is green when I put malachite green into it, but it's yellow in the other two indicators, we're going to try to figure out the tightest range that we can declare for this solution's pH. And to do that, I find it very useful to draw yourself a number line. This number line will let me kind of put down exactly what each color tells me. So I'd like you to take a moment, pause the video, and think through. If it is green in one, yellow in the other two, what are the ranges that each of those colors corresponds to? All right, we'll start with malachite green. When malachite green is green, that means that it's undergone this first color change, so it's at least 2, and it hasn't hit its second color change yet, so it's below 11.6. Now, if it was in a color change region, I'd expect to hear yellow-green or very light green. I'm just getting green, so that tells me it's in the middle of these. And so malachite green tells me that the pH of my HNO2 is definitely somewhere in here. Not terribly useful by itself yet, but let's go ahead and keep going. Cresol red being yellow tells me that it is at the very highest a pH of 7.2, but definitely underneath that or equal to it. can't be anywhere above 7.2. It would already be showing some of this red in solution. And if it was anywhere close to 8 or 9 or 10, it would just be red. So I can now take Cresol Red and say that in this range, Cresol Red is yellow. Now notice, right now, these two don't completely overlap with each other. Everything from 7.2 up is consistent with this indicator, but not this one. So I can toss it out. Everything from 2 down is consistent with Cresol Red, but not with Malachite Green. So I can toss that out. So for now, I can say it's between 2 and 7.2. But Bromphenol Blue is going to let me narrow it down even further. Because Bromphenol Blue, being yellow in color, tells me that the pH of my HNO2 has to be 3 or lower. And so if I put that in here, now what I'm looking for is the only spot where all 3 indicators are the color that we say they are. And that is only here between 2 and 3. Any pH outside that range and one or more of those colors would be different. And so that lets me lock it down and say that that's the pH I'm looking at, something between 2 and 3. It's the only range consistent with all 3 of my colors. Now, when you start with your lab, what you're going to be working with are these 3 indicators. Bromocresol Green, not Cresol Red, not Bromphenol Blue, but Bromocresol Green has its color change between 4 and 6. And so take note of these colors. If it looks like this, it means that the pH is 4 or lower. If it looks like this, the pH is 6 or higher. If it looks like this, you're probably right on 5. And if it's a little bluer, maybe it's between 5 and 6. A little yellower, it's between 4 and 5 because you're within the color change region. Phenolphthalein has this look. It goes from colorless to that dark pink. And if you've got a light pink, you're somewhere in the middle of that range. Again, clear doesn't mean the pH is 8. It means it's 8 or lower. Dark pink doesn't mean it is 10. It means it's 10 or higher. Light pink means I'm within the color change region. Lastly, we've got bromothymol blue right here. Not bromphenol blue, but bromothymol blue. And this one's got a color change between 6 and 8. Again, yeah, that's right. Again, under 6 if it looks like this, over 8 if it looks like that, 7 if it looks like this, and you can even interpolate. If it's a little bluer, it's closer to 8. If it's a little yellower, it's closer to 6 than being smack on at 7. My hope here is that all of that is going to allow you to determine the pH of the unknown that I have provided for you in a zip file. So what you're going to do to begin this lab is you're going to download that zip file. You're going to grab the one that has your name on it, your last name, and you're going to analyze it. You're going to look at your 3 indicators in order right there and tell me what pH must your unknown be if it has those 3 colors in those 3 indicators. And just so you know, it will be left to right, the same as what I showed you a moment ago. It's going to be the Bromocresol Green, followed by the phenolphthalein, followed by the bromothymol blue.